Okay, in this section we're going to be using combinatorics to calculate probabilities. Combinatorics is basically counting techniques. Specifically, the three that we've developed so far are the fundamental counting principle, as this first one, the permutation rule, and the combination rule. Now these two, the fundamental counting principle and the permutation rule, are not exactly interchangeable. But anytime you're using the permutation rule, you could also look at it using the fundamental counting principle, but not vice versa. So any one of these could be done using the formula for permutations or as a fundamental counting principle problem. We'll see this in a little bit more detail later. So basically the three types of problems we see so I'm generalizing the problem when selecting a group of R objects from a group of N distinct objects. So pick 3 students out of 20. The R would be the 3 and the N would be the 20. So if repeats are okay, we use the fundamental counting principle or the fundamental counting rule. And then if repeats are not okay, we have permutations and combinations. And the distinction there is with permutations, order matters, and with combinations, order does not matter. All right, so we've already established the formulas for these two. I'll go to the last slide. So this formula for permutations here and the formula for combinations here using the factorial notation, these we've already established. So now we'll put them into play. Let's look at a few problems that use one or a combination of these rules. Okay, so first problem. What is the probability of being dealt a hand of 5-card poker, so just 5 cards, from a standard 52 card deck? And that card contain 4 aces. So basically, you're dealt 5 cards. What's the probability that 4 out of those 5 cards are aces? All right, so let's approach this systematically, break it down. What are we given? What do we know? What are we looking for? And what formulas must we apply? So how do we calculate probabilities? So first of all, this is step 1. This is going back to the first section of the chapter, definition of probability. Number of ways your event could happen divided by the total number of possible outcomes. That's why probability comes down to counting. You have to count 2 things. You have to count the size of 2 sets or 2 groups. In this case, you have to count how many 5-card hands are there that have 4 aces. That's the first number. How many hands are there in total? How many 5-card hands are there in total? That's the second number. And then the formula for probability is you divide those 2 numbers. Next, what do we need to count? Okay, so here our event is there are 4 aces. So this is what we're looking for. The probability of this happening. There are 4 aces among 5 cards. So like I was just saying, the definition of probability says the probability of this happening is the number of ways it could happen, so the number of hands that contain 4 aces, divided by the total number of possible hands. All right, so these 2 things we have to count. And now, what counting rules must we apply? Going back to the earlier slide, we have the fundamental counting rule, we have permutations, we have combinations. So in this case, what counting rule must we apply? Well, here's our 5-card hand. So we're picking 5 objects from a group of 52 objects. So here's our N, and here's the R. So out of 52, we're picking 5. And order doesn't matter because it's a hand of 5 cards. So if you're just picture you're dealt 5 cards, the 5 cards you're holding, if you shuffle them up in your hand, you change the order of those 5 cards, it's not a new hand. It's the same 5 cards, just in a different order. So order does not matter, but there's no repeats. You can't be dealt 2 of the same card if you're just using 1 deck of cards. So this is a combination. And now what is the probability? Well, we have to count 2 things. How many possible hands are there? And how many of those hands contain 4 aces? So let's start with how many 5-card hands are there. So let's answer this question. How many 5-card hands are there? So like I stated earlier, N is 52, R is 5. We're picking 5 out of 52, and how many combinations of 5 cards are possible? So according to the formula, you'll plug in a 52 for the N and a 5 for the R. So according to the formula, 52 factorial divided by 52 minus 5 factorial times 5 factorial. And I went one too far. 52 minus 5, this gives you the 47, and then the 47 factorial is actually 47 numbers, 1 times 2 times 3 times 4, all the way up to 47. So the 47 factorial, so this is basically 1 through 47, 1 through 52. So the 52 factorial contains the numbers 1 through 47. So the 1 through 47 on the top cancels with the 1 through 47 on the bottom, leaving you the 52, 51, 50, 49, and 48. Okay, so those are after canceling, those are the numbers left, and we still have this 5 factorial, 5, 4, 3, 2, 1. So pop those numbers into the calculator. You'll get the 311,875,200 on top, and the 5 factorial 120 on the bottom. When you divide those two numbers, you get exactly 2,598,960. So that's basically the sample space of this experiment. There are just under 2.6 million possible 5-card poker hands. So that's in the formula for probability, that's the denominator. Now we need to know how many cards, or how many 5-card hands contain 4 aces. Oops. This should say 4 aces. Can't have 5 aces. Well, we could calculate the probability of that. Remember, the probability of an impossible event is 0. So if you said, what's the probability of a 5-card hand containing 5 aces? Probability is 0. Let's go back to the 4 aces. So that 5-card hand, it's got to look like this. 4 aces and some fifth unknown card. So how many options are there? The ace, 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 that's fixed. That can only happen one way. And there's 48 cards left in the deck. If you take away the 4 aces from the 52, you're left with 48. So 48 possible hands, because we have 4 aces followed by a 5th card, and we have 48 options for that 5th card. All right, so now we've got both numbers here. We've got the numerator, number of hands that contain 4 aces, that's the 48. The total number of possible hands, that's the 2,598,960. The counting's done. To calculate the probability, we divide those two numbers. You pop that into the calculator, you get this decimal, and we can multiply by 100 to get the probability. Very, very low probability of being dealt 4 aces. Okay, another example, combination lock. So here's a combination lock with the numbers 1 through 40. Actually, well, 0 through 39, but we'll call it 1 through 40. So there's 40 numbers. Oh, no, it says 0 through 39. Yeah, so we have 40 numbers on it. Find the probability that if the combination to unlock consists of 3 numbers, it will contain the numbers 1, 2, and 3. And this is important. Numbers can't be repeated. Okay, so again, probability comes down to counting 2 things. How many ways can your event happen? So our event is, our combination contains the 1, 2, and 3. So numerator, how many ways could that happen? Denominator, how many total possible combinations are there? All right, so again, what type? So we have to count these two sets, right? So what counting technique will we use? What counting formula will we use? The question is, well, there's 2 questions. Are repeats okay? Yes or no? Does order matter? Yes or no? It's a combination lock, so it's not going to open if you put the numbers in the wrong order. So order matters. That's one. And repeats are not possible. That's two. So order matters, no repeats. So the number of lock combinations is a what? And it's a little counterintuitive due to the name, but this is actually a permutation. So the number of combinations on a combination lock is not a combination, it's actually permutation. All possible permutations of three numbers where those numbers are all 0 through 39 with no numbers repeated. Okay, so we'll just use the formula for permutations. N is 40, there's 40 numbers to choose from, R is equal to 3. So how many total possible combinations are there? That's going to be the denominator when we calculate the probability. So according to the formula, n factorial divided by n minus r in parentheses factorial. So 40 factorial over 37 factorial. The 1 through 37 on the bottom cancels off the 1 through 37. That's part of the top, leaving the 38, the 39, and the 40. Pop that into the calculator. 40 times 39 times 38 gives you 59,280. So this is the total number of combinations using any numbers in any order with no repeats. So now the question is, how many ways is our event possible? How many different combinations contain a 1, a 2, and a 3? So we're taking three distinct objects, and the fundamental counting rule says there are n factorial different ways to arrange n distinct objects. So here we have three objects, the numbers 1, 2, and 3. So there should be 3 factorial ways to put them in different orders or rearrangements. So 3 times 2 times 1 is 6. So there should be 6 possible ways to reorder the 1, 2, and 3. And there are 59,280 possible combinations. Again, put that into the calculator. We get this decimal. And if you want to convert the decimal to a percentage, we multiply by 100. Here I rounded it to 3 places. Well, rounded this to 2 places. If it was 3, it would be 0.010, but we don't need that last 0. Okay, so there's an example of a permutation problem and a combination problem. I'm going to go way back to the beginning of the notes, and I think this is an important slide here. When to use what. Once you know exactly what to do, usually the hard part's over. Then just the calculations follow. But reading a problem, interpreting it correctly, determining what it is you're looking for, what it is you know and don't know, and in this particular setting, what counting technique to use. Fundamental counting rule: if repeats are okay, permutations and combinations if there are no repeats. Remember, combinations, order doesn't matter, permutations, order does matter. Okay. That about does it for this set of notes.